Our next speaker is Michael Gullans, who wears many hats. He's an adjunct assistant professor in the Department of Physics, Department of Computer Science, and Institute for Advanced Computer Studies at the University of Maryland. He's also a physicist in the Nanoscale Device Characterization Division at the National Institute of Standards and Technology, or NIST. Today he's going to be presenting about complexity, compilation, and verification of logical qubit random sampling.
Okay, well, yeah, I guess I'll just get started. Thanks for having me at this workshop. So let me connect this to Ken's introduction to the RQS by explaining how this fits into the, the sort of RC and why this work fits into RC2. So, I mean, really in this work, we are trying to also think about large-scale quantum simulation. So I would say complexity, compilation, and verification are really sort of RC1 and RC3 topics. And then the reason this is being presented in the RC2 session is because we're thinking about these questions really in the context of error-corrected circuits or logical qubits where noise is central, and also the constraints of quantum error correction enter into the consideration. Okay, so picking up where Jeff was where Jeff left off, is that we sort of, people who work on quantum simulation and other problems in quantum computing know at this point that for really many useful large-scale problems, it looks like we will need millions of physical qubits with extremely low logical error rates to get really compelling applications. So these estimates that are shown here are for Shor's factoring algorithm, but you run into similar estimates when you think about simulating quantum chemistry or lattice gauge theory or things like that. And so there's sort of two central challenges in building error-corrected quantum systems. So one is a sort of classical control problem. And so essentially, in order to realize error correction, you need this huge amount of redundancy, and you need a lot of classical control to realize that in a programmable way. So in classical computers, there's been a lot of nice innovation where basically people have been able to reduce the amount of control for controlling billions of bits down to very small numbers of classical inputs. Quantum computing has tended to move in the opposite direction, where you sort of use many wires to control qubits, and that leads to just an intrinsic scaling problem. So there's the first problem is just this difficulty of classical control, which is more of an experimental challenge. The second challenge is more fundamental to error correction, which is that once you have sort of encoded quantum information in a logical qubit, it's delocalized across the system, and it's very difficult to operate on. So the way that you think about quantum algorithms and quantum computation has to undergo a shift when you're working with logical qubits instead of physical qubits. This is arguably more of a theoretical challenge. So because of these reasons, there's sort of these large overheads in the complexity of implementing logical circuits. Most of the studies have focused on relatively small systems of 1 or 2 logical qubits or gates. And so in this work, we'll discuss some steps. We'll present some results on moving to larger scale systems with logical qubits. So before I get into that, I want to say a little bit more about motivation for this problem, which is this idea of fault-tolerant compiling. So when we think about sort of full-stack quantum computing problem, where you're going from the bottom layer, which is the physical hardware, up until through the control schemes, quantum error correction, logical qubits, and ultimately the quantum algorithm you're running. It's this sort of complicated process. And traditionally, the way that people have looked at the last layers of this stack, which is the fault-tolerant problem, is sort of abstracted away into a mathematical problem where you optimize sort of the circuit depth and the T count. And that's actually a very fruitful way to study this problem when you're looking at very large scale quantum computing problems or quantum simulation problems. But what I want to argue today is that in the sort of foreseeable future, sort of more near-term fault-tolerant systems, there needs to be much more of this co-design of the quantum error code with the hardware and also the application you have in mind. So I think Jeff in the last talk gave this very nice example of thinking about how erasure conversion at the very bottom of the stack ends up informing the higher layers of the computation. We're sort of trying to look at a similar perspective in this work. So it's really exciting to me. So I often come more from a solid state qubit background, but I've recently come back to AMO systems, and what's very exciting is that they have this sort of flexibility that maybe isn't as present in solid state systems, which is you have extremely long coherence times, and you also have very long range connectivity that you can engineer through different methods, either involving photons or through this qubit motion. And this just gives you a much larger playground to explore approaches to quantum error correction and quantum algorithms that you're a little bit more limited in other platforms. But the hope is that these kinds of efforts on AMO systems, which tend to be smaller scale, will ultimately inform efforts on all platforms. Okay. So now let me get into the sort of more technical part of the talk and tell you about the specific problem we're going to be compiling and studying, which is logical qubit random sampling. So we've actually already heard this beautiful introduction to random sampling problems in the RC1, so I can sometimes borrow from some of that material. But let me first start with the sort of hero on the hardware side for this talk, which is as we just heard about in Jeff's talks, these reconfigurable atom arrays. So the basic idea is that we have an array of rubidium atoms in this case, which are trapped with optical tweezers, and that gives us a huge reservoir of qubits where we can do single qubit operations. The challenge is to do 2 qubit gates, but the way that that's achieved in this approach is that you actually just physically redirect the laser beam so that the atoms come close to each other, and then using the Rydberg interactions, you implement a controlled Z gate, a diagonal gate. And what's nice about this is because you're building on these kind of well-established optical tools, you have a really huge amount of parallel control that goes into this, so you can actually control many qubits with just a few wires, so connecting to this classical control problem. So with that in mind, with this kind of approach to systems in mind, let me tell you about the kind of logical quantum processor design. So the idea of this work is that we're going to think of a model for quantum computation where you have small code blocks, which you're going to operate mostly on with transversal gates and sort of parallel operations. So we're not encoding all of the logical qubits into one giant code block, but we're sort of just thinking of them as these separate blocks. So to do single qubit operations, you just do this very simple parallel operation where you apply the gates on one block, and you can implement logical gates. When you want to do an entangling gate, you actually just do a transversal gate, so you move the whole block over and then apply a global pulse to implement the control gate. And that can be applied everywhere, but it only affects the atoms when they're near each other. Okay, so now we've done a 2 qubit or 3 qubit circuit. Okay, so this is the architecture that the group at Harvard and MIT designed to implement this in the system. So it's sort of a zoned architecture where you have the storage zone, you would do 2 qubit gates, entangling zone, and then you have a readout zone where you make measurements and do feedback. Okay, so that's sort of the the hardware side. So that approach to designing the hardware actually significantly reduced the amount of control that needs to be achieved in the system to get logical circuits. So now the question that we wanted to study is, given that these transversal operations are easy and natural for this system, can we actually do anything interesting or potentially useful with just transversal quantum computations? And what's maybe well known to people who work in error correction is that there's something called the Easton-Nil theorem, which says that if you only have transversal gate operations, which means you apply the same gate to sort of every qubit in the code block, then there's no universal gates that you can achieve for any distance greater than one code, any error detecting code. And what that means is you're restricted in this setting to a subuniversal model of quantum computing. What it turns out you can do, though, is this what are called IQP circuits. And to see that, it's enough to sort of present one code that achieves that. And so there's actually this family of color codes called hypercube codes. So they have parameters 2 to the d, d2. So d is like a spatial dimension. And they encode capital D logical qubits. So with these are what are called CSS codes. So you can do state preparation and measurement in the X and Z bases transversally. You can also do C0 gates, and then what's particularly special is you can do in-block diagonal gates. And if you have a way of doing Hadamard gates, you have sort of universality. So the sort of smallest interesting example of this is the 832 code, so capital D equals 3. So this is a code which lives on a cube. These are the stabilizers in the top. And then the logical gates you can do in a transversal way are illustrated on the bottom. So there's this, so the CCZ gate is a non-Clifford gate, so that involves physical T gates. And then you can do these other Clifford gates that are listed there. Okay, so the natural gate set that we have for the system then is Z gates, ZZ gates, these CCZ gates, which are non-Clifford, and then also C0 gates. So there's a simple observation, which is that if you implement this gate set on a generic set of qubits, it's actually just equivalent to a pure IQP circuit with just diagonal gates, but on a different graph. And what you can show is that this color code family that I introduced previously allows you to perform sort of arbitrary degree D IQP circuits. So degree D just means the highest degree of the CCZ gate involved. And what's known from results in computer science is that if you sample, so sampling from random degree 3 circuits is classically intractable for complexity theoretic reasons. Another interesting perspective on random circuits is that they let you sort of benchmark the quantum processor as a whole. So they're used as a way of benchmarking fidelity and verification of your processor. So the sort of next ingredient that we need, so we have this universality result for IQP circuits, and now we want to sort of compile that into a hardware efficient algorithm or circuit family that we can run on the system we have available. And what we came up with was to actually run IQP circuits on a hypercube graph. So what's going on here is we scale up the system by connecting larger size hypercubes. So we connect these hypercube codes into hypercube graphs where the edges denote C0 gates. And maybe just to illustrate it much more concretely for the case of 4 blocks, so this is what the type of circuit we would be studying looks like. So what's going on in say each individual row of 3 is we're applying random IQP circuits within the block. Then we're connecting those blocks in this hypercube architecture with the C0 gates, and then we proceed through the evolution in that way. And at the end of the circuit, so in IQP, you measure in the X basis. And that's the random circuit family. there's a detail which I'll actually explain in a little bit, is that these circuits, we include also permutation gates, so not just transversal operations, but also permutation operations. The experiments that have been reported so far didn't actually have those permutation gates. So here's a nice movie which illustrates the circuit. So in this first step of the movie, we're encoding the 832 code. And then now at this point in the movie, we're actually running the logical circuit using these transversal operations. So in that first round, we created one three-dimensional cube. Now we're creating another three-dimensional cube over here. And then in the final step, we're going to form the four-dimensional logical hypercube. So this is an example of a 48 logical qubit circuit. Okay, so so that's the sort of overview of what we're studying, and now I want to dig more into the details of how we characterize this problem. So what we're thinking about in this setting is specifically complexity and benchmarking with random circuits. And what we're going to be studying is this output distribution P sub c of x. So this is, you start in the x basis, you apply an IQP circuit, and you measure in the x basis, and you get some random outcome. And we want to understand that distribution. There's sort of two ways that we characterize this problem. So one is that we're looking at scrambling and something called anti-concentration. One way you can actually measure both these quantities is by looking at something called the average collision probability. So you look at the sort of expected value of this PC, so the average of PC, which is the sum of x PC squared. And when this is small, that means that the sort of output distribution is spread over many bit strings, and that's when we expect classical computation to be hard. So this exponentially small collision probability indicates that you have information spread non-locally across the system, and you also have hardness of sampling. The other type of quantity we're very interested in is something called the average fidelity. So here it's similar to collision probability, except you instead look at the overlap of the sort of ideal state, now quantum state, with a noisy implementation of that circuit. And so that's another sort of two-copy quantity. So the challenge with the fidelity is it generally requires exponentially many samples to implement. And so what people working in random circuit sampling came up with, especially the Google group, is this idea of the cross-entropy benchmark. So what this does is it, instead of computing the fidelity, it computes this cross-entropy between the ideal distribution P and the noisy distribution Q, and then when XCB, the conjecture is that when XCB is high, it sort of signifies that fidelity is also high in the system. The challenge of this approach, which was alluded to earlier also, is that it's computationally inefficient to actually measure XCB. And so, so there was argued, it's an interesting sort of sub-story here, which is that it was argued that XCB can be used to estimate fidelity, although it was shown in sort of follow-up work that that's not the case. There's regimes where XCB fails to estimate fidelity. In our own work, we sort of sharpened this notion to show that there's actually a phase transition where at low enough noise rates, XCB approximates fidelity, and then at high noise rates, it ceases to approximate fidelity. What this is saying at a high level is that when your noise rate is on the order of 1 over n, you're in what we call the healthy regime, where XCB estimates fidelity, and when it's at high noise rates, you're not in the healthy regime. So this really says that when you're using XCB to benchmark random circuit sampling, you have to be very careful about the noise in your system and what regime you're in. And n is the number of qubits. Right. So this is saying that it's very good that we're doing error correction, because we want to be in this asymptotically vanishing noise rate regime. Right. Okay, so another important point is just trying to understand the classical hardness of the noiseless simulation. So even assuming there's no noise, how would simulating these IQP circuits, how hard would it be? So one thing we can estimate is hardness of tensor contraction, and so we can look at something called the tree width, and that actually approaches, like very quickly in these circuits, it approaches the maximal value, so in log depth. There's another interesting set of attacks for IQP circuits which aren't really present for Haar-random circuits. So this is another problem that arises when you're doing logical computation where doing non-Clifford operations is hard. And that's algorithms which exploit low T counts in the circuit to simulate them. And so there's a family of algorithms that were discovered by IBM and IonQ which actually simulate our circuits efficiently without these permutation gates I mentioned. But so it turns out that adding these permutation gates recovers this kind of, instead of two, so this Clifford plus T simulator was a 2 to the n over 3 cost algorithm. By adding these permutation gates, you can kind of recover a 2 to the n scaling. So that's another interesting point we learned from thinking about these circuits. Okay, how am I doing on time? Just 5 minutes? Yeah, so I'll go quickly through this point. So one of the important points is trying to develop an analytical understanding of this IQP circuit dynamics. And here we're actually borrowing a lot from what we've learned from studying just generic Haar-random circuits, which are based a lot on mappings to statistical mechanics problems. So the Haar-random circuit problem can be mapped to, you can actually analyze quantities like collision probability and XEB by thinking about a spin-a-half model. There's a nice result that we've derived, which is that you can develop a similar StatMech mapping for these IQP circuits, but now it involves 4 states per site instead of just 2. So it's in some sense a richer model. So with with this kind of analytic tools in hand, we can derive a number of nice results. So we can prove this anti-concentration properties. We can compute XCB in certain ideal XCB values. Maybe one particular result which we were able to prove, which we haven't been able to prove in Haar-random circuits, is the existence of this noise transition analytically. So we can see that at low noise rates, you're in the healthy regime where XCB approximates fidelity, and at high noise rates, you lose this property. So now I can come to describe the experimental results. So what was done in the experiment is sort of sampling with error detection. So there's no mid-circuit measurements. So you prepare a logical state, you apply a transversal circuit, and then you measure in the computational basis, and you can extract the stabilizers from that, and basically by if many of your stabilizers are the correct sign, then you accept the data, and otherwise you reject it. And this plot shows the logical XCB versus acceptance ratio, and you can see that it's improving as you increase the amount of error detection. You're improving the XCB. Okay, so these are the experimental results which Ken actually nicely summarized. And so what we're seeing here is the logical XEB for 48 logical qubits, which is higher than the estimated XEB you would get from a physical circuit. So it's sort of beyond break-even performance in error detection. Another interesting set of questions we can ask is how would you scale this to larger systems? So there's sort of 2 natural directions to scale. So one is you can increase the degree of the IQP circuit, and that you can do by going to higher dimensional color codes. You can also increase the code distance, and that gives you a threshold theorem for our sampling task, which is stated here. So for low enough error rates, you can get exponential error suppression for this IQP sampling. So another nice direction in this work is you can change the task you're doing. So instead of sampling in the computational basis, you can sample in something called the Bell basis. And this actually gives you a way of measuring entanglement in the system. It also it gives you a sort of efficient verification of random circuit sampling subject to certain assumptions. And what we have been able to show is that if you have degree 4 IQP circuit, you have hardness of Bell sampling with efficient quantum advantage. Okay, so let me briefly describe the outlook. So I think, so far the experiments that I just presented, we could simulate them on a classical computer, like on a laptop. But we think there's a realistic path to classically hard sampling experiments with logical qubits. So stay tuned for that. I'm hopeful. I think this idea of fault-tolerant compilation, which has been out there in the community, but I think now it sort of motivates to look at this more carefully, which is to really start co-designing codes and hardware with actual applications. So there's many other problems you could apply this to. I think these reconfigurable atom arrays, just on the experimental side, they're very promising for pushing the future of fault tolerance in the near term. And let me thank my collaborators. So the theory work is posted on the archive. That's with postdoc at Maryland, Dominique Hengleiter, and graduate students at Harvard, Marchin and Dolev, and then Alex and Misha. Alex Kubik, who's at Yale now, and then Misha at Harvard. And then the experimental work was led by Greiner, Vuletic, and Lukin at Harvard and MIT. So thank you. Go ahead.
Could you say a little bit more about these?
Yeah, so, right, so what we've done so far is we thought very straightforwardly about like these hypercube codes and how would we scale them up to larger distance, and we've found new families of color codes that scale the distance. Actually, in recent work, that's not in this paper, we've actually understood other connections to IQP that happen naturally in logical and sort of when you're trying to make low T-count circuits. And I maybe can talk to you about that later. Yeah, but this is like very specific. It maybe not. This might not be so practical for experiments, but these other schemes, like there's sort of natural reasons that IQP comes up in logical computation, and we're seeing it in other places as well, which is interesting.
Any other questions?